Comenzamos. Muy buenas tardes. Bienvenidos y bienvenidas a la primera sesión de las Geocharlas del Servicio Nacional de Geología y Minería, Sernageomin 2025. Una función relevante del Sernageomin es generar, mantener y divulgar información de geología básica y de recursos y peligros geológicos del territorio nacional al servicio del desarrollo del país y del bienestar y seguridad de la comunidad, razón por la cual instancias como esta son coherentes con nuestra misión institucional. Es así como en el marco del convenio de cooperación que mantiene Sernageomin con el Centro Colaborativo de Investigación CRC 1211 Earth Evolution at the Dry Limit, aprovechamos la presencia en Chile de geocientistas alemanes de uno de los proyectos participantes para que nos cuenten sobre su trabajo que se enfoca en abanicos aluviales de lugares tan áridos como los desiertos de Atacama y Namibia. Aprovechamos la ocasión para saludar y agradecer a las personas que se encuentran presencialmente en el auditorio y a aquellas que están conectadas de manera remota. Antes de continuar, les recordamos que existen salidas de emergencia bien señalizadas y ante cualquier situación les pedimos mantenerse en sus lugares hasta recibir instrucciones de parte de los encargados. A su vez, queremos solicitar su colaboración para el buen desarrollo de este lanzamiento, poniendo en silencio o apagando sus teléfonos celulares. Gracias por eso. Empezamos por saludar a las autoridades presentes, en este caso el subdirector nacional de Sernageomin, señor Mauricio Lorca. Y también agradecemos a la Universidad Andrés Bello nuevamente por facilitarnos este lugar para desarrollar las charlas. Sí. Okay. Bueno, además también queremos hacer una introducción para dar contexto al CRC, que es la que, con la que comenzaremos ahora. Ahí está. Bueno, para comenzar, el CRC es un megaproyecto con sede en Alemania que está dedicado a desarrollar investigación relativa a ambientes áridos e hiperáridos, principalmente en el desierto de Atacama, aquí en Sudamérica, y de Namibia en África. Claro. Dentro de las instituciones participantes en este en este megaproyecto está el Sernageomin, entre muchas otras instituciones, tanto del país como internacionales. Bueno, y lo otro importante es que este proyecto se ha desarrollado durante 3 etapas de financiamiento, cada una de 4 años, desde el año 2016 en adelante. De esta, la última está en pleno desarrollo en este momento. Dentro de los subproyectos del CRC 1211 se encuentra el dedicado al estudio de abanicos aluviales en ambientes áridos y hiperáridos, y es en base a la visita de 3 de sus investigadores, de algunos de sus investigadores, que tenemos 3 presentaciones hoy. La primera de Frank Lemkuhl, del doctor Janek Balk y del doctor Joel Muren. Entonces, invitamos a el doctor Frank Lemkuhl para que haga su presentación. Frank, can you come?
Okay. Hello, everybody. Thank you to come to this lesson here to tell you something about our CRC and our challenges, what we want to do. My presentation is a bit broader because I worked on alluvial fans since 2 decades almost, and I want to give you an introduction. What are alluvial fans, and what are challenges, and what are advantages of alluvial fan research? So I give you an overview about alluvial fan formation in cold and warm desert. And I must tell you the truth, this was an invited talk on the American Geological Society last October. So I take some slides from that, and you see this work cannot done by myself alone. It's a big team, thanks to the Chilean colleagues, to the Namibian colleagues, and also to quite a lot of co-workers, Louis Owen from America, Joel and Yannick, you already mentioned, and also another member of staff, Dennis Wolf. Short introduction on the CRC. The CRC is, as already mentioned, a big project. In Germany, it's one of the biggest funding projects you can have. It is situated in the University of Cologne, together in association with the universities of Bonn and Aachen nearby. We have, as you already heard, 3 phases of the project. I will go to that a little bit later. And it's a big team. It's not only our team as geologists and geomorphologists. We also have paleoclimatic issues in that. We have biological effects in that. We want to know what is the biological evolution of the Atacama Desert, and how you can connect these with the geological evolution of the last 2 or even 10 million years. So if you want to have more information, I invite you to look on the CRC website. So therefore I want to go further. And we have different scales, of course, from the environment, from the local scale to the environment scale to the larger scale. In our project CO2, we are happy to be involved in all 3 phases. In the first phase, we worked on the coastal alluvial fans in the Atacama Desert, and that was the PhD of Yannick. And we have also Melanie Bartz, who makes quite a lot of efforts in dating approaches from ESR, for example. In the second phase, you see already, which starts in 2020 to 2024, we moved from the coast towards the central Atacama. I was happy that Andres can join us with this. We worked to the Sala Grande, and we worked in parallel. We worked also tried to work on Skeleton Coast, because we have only 2 coastal deserts on Earth, and that's the Atacama here, and it's the Namib deserts on the other side in Africa. And now we are in the third phase, which should come to an end of the project, and we should summarize. And so we focus a little bit more closer to the Andes, go to the fallen of the Andes and the Andes itself, to have a whole transect to the different landscapes in the Atacama Desert. You see already some satellite images. We worked in our approaches with remote sensing data. We worked with drones. We worked with also with satellite images, digital terrain models, and you see the different examples from left to right, from the coastal alluvial fans towards the interior, and last but not least to the altiplano fans. And I have a nice cross-section. The pointer is over here. A nice cross-section where that's a nice cross-section over here where you can see that we have here the coastal alluvial fans. We have no precipitation in the Atacama, and in the altiplano we have more rainfall. No? Does not work. Right arrow. Okay. So what is a main problem, and what's also differences between alluvial fans? We have different scales. We have different spatial scales, and we have also different temporal scales. So for example, let's look on the coastal fans. We know now they date to the last 100,000 years. They are small scale, and they have a smaller scale in comparison to the large scale alluvial fans, which has something to do with the mountain uplift. These are an example from the Ganges plain. The Ganges is the Himalayas. You have fans which are more than 100 kilometers long and extend very large, and they build up in millions of years. So you have the different scales. To those fans already, belongs debris flow fans, which created in every mountain system, which has high frequency, which can occur in decadal as well. And later on, I will also show you those fans which are in a medium scale, which are in a Pleistocene scale, in a scale of 100,000 year cycles. And these examples, I will bring you to Mongolia. I worked on Mongolia for about 30 years almost now. We have also a project on alluvial fans in Mongolia. And I want to bring you in this desert as a cold desert to show you what's the difference between a cold desert and a hot desert. The first main difference is that in a cold desert, you have quite a lot of snow, you have frost activity, and you have also creating quite a lot of weathering by frost, freezing, thawing cycles by frost activity. And that creates quite a lot of debris, which is available in the mountains, which then is transported by the flash floods to the mountains. So you see, everything what you need for an alluvial fan is a mountain system, which created by tectonic uplift. And then you need some sediments, which transported through a channel towards the mountain fringe. In Mongolia, this is also something to do with quaternary glaciations, because also glaciers produce quite a lot of debris and quite a lot of glacial fluvial, alluvial fans and glacial fans. Das war zu viel, oder? So I bring you to Mongolia to have examples over there. I must tell you, we just published a review which is open access together with Louis Owen, and we summarized several mountain regions. But here for Mongolia, I show you 3 examples from this alluvial fans. Maybe I skipped this a bit faster. This is an alluvial fan in the Altai Mountains, high uplift rates and different phases of the alluvial fans, and you see them in front of the mountains. And it's quite different to Atacama Desert, because here, of course, you have steppe vegetation and even small areas with north exposed forest, which is a large forest over here. Second example is in the Gobi Altai. There you have huge neotectonic events. This is one region with one of the heaviest earthquake events on Earth ever happened. American colleagues pointed out that these fault line is as active as San Andreas, and if American scientists said that, I think it should be true. And on the other hand, we have here also quite a lot of fans building in the mountain front, different generations on this active fault line. On the northern side, here towards a mountain called Hangai, we have not such active tectonics, it's not such strong uplift, and there we have also the development of alluvial fans. We date also them with the cosmogenic nuclides, and there you can see that here the fault lines are hidden by the alluvial fans. So you see that's a fight in between tectonic, making fault lines, creating new rivers, and a climate which brings quite a lot of material, which then occupies huge parts of the landscape. And the third example is the modern one. We're just working in that area in eastern Mongolia on Lake Khegasnur, where we have also quite a lot of these huge alluvial fans. And there we have also, in this closed basin, an association with lake level changes and with glaciations. And now I want to sum up these things. This is the example from the Orknur, from the alluvial fans, and you see that here some of them are dissected. And if you have a closer look on this air photo, you can see that there's a huge fan over here marked by this yellow line, and then there is an incision, and you have a smaller, sorry, the red is not very good visible, a smaller recent alluvial fan. So we have 2 periods of fan formation over here, and that has to do with the Pleistocene sheet flow, which covers all the mountains, covers all the basins, makes these huge alluvial fans. They call them pediments or bayadas or different naming for that. And then in the light Pleistocene, there is a change in climate, and we have an incision in this landscape and build up a smaller scale. And you see there is a transition in the late Pleistocene from sheet flow to debris flow, and we have different sediments from accumulation to erosion. And even in a drier climate, erosion can be stronger. So these alluvial fans need precipitation values between 150 and 350 millimeters, so they are semi-arid agents. We also date them. I don't want to go into detail. I can just tell you that all these huge fan developments belongs to the Pleistocene, to the cold phases of the Pleistocene, when the lowering of glaciers, the lowering of periglacial weathers create a lot of debris, and this debris then is accumulated in front of the mountains. And this is a cyclicity, because we have in the Pleistocene, we have a change between the warmer interstadials and the colder interglacial periods, and then we have buildup of alluvial fans, incision of alluvial fans, so we have multiple cyclicity of these fans. So here you have a clear climatic control. I come to Chile later, I come to Chile now, this is quite different. And now I want to show you the different scales from the coastal fans to the central part, to the Altiplano and the mountain front. Please notice that this will be focused in the talk of Yannick laterwards, and the second one in the talk of Joel, so I will skip this a bit faster. But please look also on the sizes. We have small scale at the coast, we have mesoscale in the coastal Cordillera, and we have this macro scale in the mountain front of the Andes. This is the cross-section once more again. So we have here this, I call them type 1 in a small scale and a high frequency. And then here the type 2 are here, and also in the Andes, which are mesoscale and which are also in a mesoscale dynamic cyclicity in 100 years cyclicity. And the type 3 are this huge, very old one, dating back to Pliocene or Miocene, which has something to do with the mountain uplift, and which are much larger. Yeah, these are these coastal fans. You can see them. Of course, here plays also the different sea level changes plays a role, and the coastal erosion plays a role. You have steep gradients, but Yannick will tell you much more in detail on this topic. We have also ages on that. I don't want to go also on the details, but please look on the timing of this type 1. It's a timing of 0.01 to 0.1 million years. So that you see what is the cyclicity, small scale, and from the cyclicity, from the timing in a very younger part. Then we come to the Sala Grande and the coastal Cordillera. We make this approaches in the second phase especially. We also make geophysics. Joel will talk on this a bit later, but please see here already the ages, which are 500,000 years to almost 1.6 million years, so which are which can be good connected to the evolution of the Sala Grande. After the Sala Grande, we need still to discuss where the debris, where the material comes from. Is this also developed by the sea, by the fork, which comes sometimes in this interior and with the Loma vegetation together also created some weathering. We can discuss this later. So, and then come to the mountain front where we have this where we have this huge alluvial fans dissected and also tens of kilometers long. And they date after Evans star up back to 20 million years. So you see you have a timing of these huge fans, 4 million years to about 20 million years. So you see quite larger in scale and also larger in the timing, in the time range. So to summarize, we have 3 types: small scale, which are younger; mesoscale, which are medium in the age and in the size; and then the large alluvial fans, which dates back with the evolution of the Andes, which dates back millions of years. Well, and now in our now field work, which we're now approaching, we want to look on those on the Altiplano. I think we have the hypothesis that these are also in phase with the quaternary cyclicity, like on our fans in Mongolia, because here we have also Pleistocene glaciation and periglacial weathering. Just to sum up, the alluvial fans in deserts are one of the most common fluvial system and landforms, which you can see in these deserts, in cold deserts and also in the hot deserts. They are often associated with mountain uplift, with steep mountain fronts. They are often created and also modified by tectonic. So therefore they are not a very good archive for say something about the climate. The Pleistocene periglacial sediment production, the frost weathering, is very important for those in cold deserts. By the way, even for those in Death Valley, which you maybe know as one of the famous one with alluvial fans. So these fans in cold deserts can link to the climatic variability, and the autocyclicity plays an important role for this development for the development of these alluvial fan systems. In the warm deserts or hot deserts, like in Chile or in Namibia, the fans are dominated by debris flow and sheet flow, and sometimes also associated with strong weather events, as we had in Antofagasta quite some years ago. And in the central and hyper-arid coastal ranges and in the Atacama, they are sheet flow dominated, and they are all dated up to now, most of them dated to mid-Pleistocene. And those in the mountain front are much older and date back to the Pliocene or Miocene, these large alluvial fans. So here, different temporal and spatial scales occur, and these autocyclicity, like in the cold desert, does not play such major role, because these deserts are always hot and cold. We developed a triangle to see the extreme weather events here, the small scale one, to see the type 2 with the quaternary cyclicity in here, and to see the large scale here, and you see increasing size and time plays a role. So I don't want to go into detail here. I think we can discuss this later on. What we just found also out that we have also, as let's say, a fourth type of alluvial fans, and that are those of old landscapes, like the Gondwana land surfaces in Namibia and in Australia, date back to the Cretaceous. There you have very low sediment supply, and there you have also very old systems. We call them type 3 slash, and expand our triangle to that. And therefore, for the Salagrande region, I now think maybe they are not type 2 with the cyclicity. They are maybe also associated with this long-term evolution like those in Australia. So to have a global perspective and look on global examples, we can also have some more insights on the development on the Atacama fans here. And we like to discuss this, and we also produce some further data on that to come closer to that. So in my last slides, I just want to make a short outlook what we will do in the last phase. We will look for on the alluvial fan of the Altiplano. In addition, we try to synthesize, and we want to come to landscape modeling. That's one of our aims also of the CSE, to show how is the evolution of landscapes. Now I need the computer screen, because you can click there and then this will move. I don't know how to do this from here. On the laptop you can on the slide you can just click here, and then there's a video. It's a video inside. Anyway, this is a model which is done by Amanda. He's from the group of Jean Braun from GFZ in Potsdam, and she will make alluvial fan modeling in different scales and in different approaches. So we have a transport limited system, and then we have get diffuse models, and we have also supply limited systems and under capacity models, and we make laboratory examples and also numerical examples. And sorry that I cannot start the video. Maybe somebody would try just, but it shows you just an up and down in this movement of the fans, and we try to model this. Now it works. Okay. Yeah, so you see here, this is the age in million of years. This landscape modeling goes back to the Pliocene and Miocene. And of course, we also need to testify how these models work. So we take also samples for grain size and for dating to testify these models. And of course, models gives us ideas how these landforms in Atacama and also in Namib developed in the different scales, in the different time scales, and also in the different spatial scales. Oh, so that's the last slide. this is our field trip where we want to go now, and thanks also for the Geological Survey of Chile that they provide us material, that provide us help, and that even Andres can go with us in field. We really appreciate that. That's a great help for the project, and we hope also to get some more data which we can share with you from the evolution of the Altiplano and also of the fans in Sala Grande. So we will go here on the Altiplano getting some stratigraphy, chronology and structures. We also tried some geophysics. We take some further samples also from grain size for the models. And at the end, we take drone surveys and have Amanda with us as a postdoc who will try to make these landscape models, and another PhD student, Julian Krieger, who will also work on these details. So I thank you for your attention, and I'm happy to answer your questions. And of course, this work was not possible with quite large teams working together and with funding from German Science Foundation and different agencies in Namibia, in Chile and Germany. Thank you very much.
Gracias, Frank. Hay tiempo para preguntas. ¿Alguien que quiera consultar algo? ¿No por ahora? ¿No? Frank?
Yeah.
The actual program for your field trip is very ambitious.
Yes.
Yeah. Yes. It's principally, do you want to take data for modeling and prove the previous results?
Yes, we make Julian, especially Julian, makes quite a lot of research before and screening on satellite images on the different sites and on the different locations. And also we are in contact with you to ask for the geology, because as we all know, if you want to date them, you need good quality of quartz. And we have quite a lot of volcanoes over there, which might be not suitable for dating. But maybe others are much better for the landscape modeling, so we will just see. And we take with us geophysics, as we want to know what is the thickness of the Alluvial fans. You see the model, so all these things goes in the models, and of course models are always, well, I will not say I'm always wrong, but are always an estimation to give us some ideas how the landscape will develop over these long time periods. So this disadvantage in geosciences is in contrast to physics. In physics, you make an experiment and you just see after milliseconds what happened, but we have millions of years. So we just try to estimate, and we have quite a lot of estimations over there. But I think we can try to get a bit closer view to all these systems in the Atacama.
And do you expect to make similar work in Namibia?
Well, the CRC concentrated now on Atacama in the third phase. That was only an idea to bring these ideas also to Namibia. Me personally, I would like to go one time back to Namibia, because there we have very good and similar results. There we have also these very old fans, which can be really good, a very good comparison to those of Chile. And we have only 2 field trips, and I think in Chile we were 5-6 times, I don't know exactly. And well, we have 3 more years, and we will decide next year. But the problem is now that even in Germany, the funding is reduced by 5%. And we need to look at, especially travel money is reduced quite a lot. So we will see what we can do. But Namibia would be very good, but maybe we come next year back to Chile again.
Okay. Another question?
Thank you, Frank. What is the principal difference between the alluvial fans in cold and hot deserts? Maybe the timing, what is faster, or the quantity of huge fans?
A little bit both. one thing is you get quite a lot, much more material in the cold deserts. So, for example, there were drillings by Chinese oil industry in the Tarim Basin, and there we have 6 kilometers thicknesses of alluvial fan deposits, of course, over 6 million years, but anyway. And they are really enhanced by this strong weathering by periglacial and glacial activity, which are going down. So the glaciers move down in the Pleistocene and create quite a lot of debris, and these is in these huge alluvial fans that cover all the landscapes. If you go to Chile, they have a very thin cover. So these in Sala Grande, they're very thin, and they have not this this cyclicity. You know, in Mongolia, we can see, well, this is last ice age, this is penultimate ice age, so we can really put our fingers on and can see that especially during the last 2 glacial cycles, huge amount of debris is produced. Of course, the older ones sometimes are covered by debris or are bulldozed by glaciers, but there's much more material and much more this autocyclicity.
Entonces, si no hay más preguntas, le agradecemos. Thank you, Frank.
Yeah, thanks.
Now, Janek Varg will give us his talk.
Thank you, Andres. I'll just wait, of course, till the presentation switched. In the meantime, thank you for giving me the opportunity to talk here at the Sernageomin. Mostly, I'm, during the past 7-8 years, always just traveling through Santiago to the north, largely. But of course, knowing that one of our most important partners is stationed here in Santiago with the Sernageomin. So now I'm really happy that this time we found the opportunity and take the day here to come here and present our results, basically from the last 2 phases and more than 8.5 years. This is Joel's now, that will be the 3rd one. There should be another file. Yes, this one, that's it. Thank you. Okay. So, yes, I'm Janek Valk, and I had the pleasure working since the first phase in CRC of the sub-project CO2. I just summarize it, transport and deposition. So, during the first phase lasting until 2020, I did my PhD in Aachen in a group of Frank. And but also it's opportunity to continue some research in the following years. So that's today what I'll present here is a summary of the last around about 8 years, but more from our research at the coast of the Atacama Desert. And I titled it basically the talk like my dissertation in the end, so the subtitle Landforms, Processes and Evolution, and that you will see during the talk that's also kind of what structured it and the different elements, and also by, let's say, complexity, what was at the end the most difficult to grasp, the actual evolution and the controls on the evolution. So just to bring you very shortly back to the Atacama Desert, as you're well aware, and notes also during Frank's talk, it's specifically characterized by its hyperidity, and one can even see, I mean, basically the entire Atacama Desert, including the coast, is hyperarid according to an aridity index. You see here at the southernmost part of the Atacama, here at Paposo, 25 degrees south, longitudinal transect of only 25-30 kilometers from the coast inland. And here in those coloring from yellowish to red, you see the aridity indices. And here you cover already, you change from going to the coast inland over 1 order of magnitude within hyperaridity. So in the core, you have some kind of very extreme hyperaridity, while at the coast, here and especially at the south, that's why I picked it, it's a microclimate at Paposo, which is a bit more humid, so you can have maybe up to 30-40 millimeters of mean annual precipitation. but nonetheless it renders it hyper-arid, but yeah, you will have way less, practically up to 0 or just a few millimeters inland. The other big gradient you have is additionally a latitudinal one. It doesn't seem so prominent as the one from the coast inland, but it is indeed. So you see it, for example, here, landscape photo of the badlands in the upstream catchment of the Quebrada de Pica, which drains here. Here in the map it's Rio Seco, doesn't matter the actual name, but you see it's completely barren, the landscape. And you've got this, yeah, with the gypsum, the fossilized landscape. Further inland, yet Aroma fan, one of the big ones coming from the Andes, you will even find those very massive gypsum polygons as one, I would maybe say one archetype, landform formation, very specific to this extreme hyperidity. Now, why is this on the one hand so interesting and renders such a long tradition of research relevance? Let's say on the one hand, we have here now an end member of a non-polar dryland environment on Earth. And when we look at global projections, climate projection, we do have indeed quite a lot of areas which are projected to develop from an arid into an hyper-arid state. So the understanding the Atacama Desert gives us a sense of how might landscapes develop if we really push it to an extreme with the aridification and desertification. Another point is that the Atacama Desert is used a lot as an analog for Mars, the most accessible we have on Earth without actually going to Mars. But another important one, as you're well aware, especially from the Sernageomin, is richness of natural resources. Might be evaporitic nature or by the bedrock geology, the ores, the metallic ones. Here an example from a study which also used the nitrate deposits as a long-term marker of hyperidity. So a lot of those extreme accumulations of the evaporites only could develop during this long-lasting hyperidity. Now, that is basically, let's say, the state of the Atacama Desert, how it's usually subsumed, including the coast. However, what I want to convince you today in the talk is that it's worth to decipher the coastal environment. I mean, it's a very spatially narrow environment. Usually the coastal plain is only maybe 1 kilometer, maximum 3 kilometers wide, but it is a very distinct one, very distinct from the inner core of the desert. And here are 2 more pictures, one very north, already out of this map, at the Bay of Pisagua, again, very barren. Here you have barely any coastal plain, so this coastal escarpment dips almost right away into the ocean. And you also see that this cliff is barely not dissected at all. And then you have here the cliff, how it looks at Paposo. On the one hand, you notice the vegetation, the Loma vegetation, but you also see if the resolution would be higher that there are a lot of alluvial fans. And what makes one big difference is, apart from those slightly higher precipitation at the coast, is specifically the high frequency and occurrence of the fog. So daily you have the fog incoming, and this is what mostly also the Loma vegetation feeds on, less the precipitation. And this, of course, is an important factor we need to consider, for example, as Frank nicely mentioned, as how does this, for example, might affect sediment production or stabilization on the other hand with this vegetation. Now, what we find a lot at the coast are, especially now speaking from the point when we started the projects, are unknowns. So a lot of research has been, due to the research relevance, focused on the core of the desert, but not much on the coast. One example in geoscience might be also embedded in the alluvial fans, I will notice later, but the alluvial fans themselves, which we find here frequently, have barely been studied. But we were quite sure it's because it's the most important archive, fluvial archive we find there, that we can use them as a geo-archive, serving information about the environmental conditions in the past. And by principle, an alluvial fan here, you see a scheme, should be a very promising archive because its depositional body is right away attached to its source area. There's not like with a big river system, a lot of pathway in between maybe the deposit of the delta and its actual source area. So there is not much transport way to shred the environmental signal, theoretically. Of course, this can happen to some degree within the catchment. But nonetheless, so yeah, why not using them? And what we especially make a lot of use of is that we have those different generations which develop in alluvial fans. So, and I'll introduce this nomenclature here because this will reoccur in my talk and also then in Joel's. So here you see an example of a progradation event. So basically an alluvial fan after some time incisors in its own sediments, and just also by more stream power law, and it's more energy efficient to now incise and prograde, has enough sediment supply, and then deposit a new active lobe in the front. And by doing this, by incising in its own deposits, the older one is abandoned. And so I will talk a lot about those abandoned surface generations. And this we can then term, for example, Q1, or this might be now a typical American nomenclature, that where you count the younger ones, there might be a third one upcoming, always with an additional number. There are also more the European nomenclature, where always the youngest one is 0, and then you count upwards the older you get. So just don't be confused if you find either of those. Now, what were now our big research objectives and questions to answer with those alluvial fans? Now, what can we analyze? What do they offer the fans? So they have certain characteristics. You can group them as a surface morphology. There's the stratigraphy of the coastal alluvial fans, but also the morphometric attributes of the catchments, as well as spatial trends in those characteristics. And what principally affects them, how they evolve, is a combination of external or allogenic environmental controls, summarizing climatic, geologic, might be both lithology and tectonics, and biotic controls. But on the other hand, also intrinsic, chaotic controls. We cannot so easily link and explain, but they're, especially in alluvial fans, very important. So those will affect our characteristics, and in the end, we want to use them and those characteristics to extract information about especially those allogenic controls, if we can decipher them. And those are the archive functions which I summarized here. So on the one hand, that is the magnitude and frequency of the primary processes, the processes building the fans up. Then you have the process, or the archive function of the timing of the development. When did that happen? And under which time of cyclicity. Then we have secondary processes, meaning after the deposition, the post-depositional alteration can be by weathering and or soil formation. And also to some degree, they can be used for to derive coastal tectonic uplift. And that is the example which has been done prior to start of the project there. So the alluvial fans, which were analyzed at the coast, were targeted especially for intercalated marine terraces, which got uplifted. If you can date them and refer the transgression peak in elevation, you can use it to derive the uplift rates. I mean, of course, it's an average over this time, but it's directly inferred one. So our research objectives basically directly can be drawn from those archive functions with the magnitude, frequency, and types of the primary processes, and to understand and decipher the relative importance of those allogenic controls, the timing of the fan development and paleoenvironmental implications, and in the end also, the last part, processes and rates of weathering and soil formation, which could be deduced from those fans. I'll start with our most important results regarding the types of the primary fan processes. And so this, what you see here, is a detailed geomorphological map of first results I gathered during the PhD research. I basically took the effort to create this high-resolution or large-scale geomorphological map of the coastal alluvial fan complex Guanios. It's just north of Tocopilla, for the reason that it is among the morphostratigraphically most complex one which we can find along the coast of the Atacama Desert. So it is also an extreme example, but it very nicely preserves here in the shape which processes develop them. So you can nicely see debris flow levées which are preserved several generations in the topography, apart from the super prominent Holocene coastal cliff, which you see also here in the picture, exceeds in those central parts over 40 meters. So it's also such an extreme example because of the catchment constellation. The coastal Cordillera in this area is extremely high. The Cerro Tolar there reaches over 1,700, 800 meters. In other parts, the coastal cliff is not that high, the escarpment. And the catchments are small, so very steep and small. We did not only created this morphography to derive the primary processes from the landforms, but also to construct the first morphostratigraphic model. So yeah, which of those surfaces evolved after each other to get a first relative chronology and idea. The other part which we use to derive the primary process is, of course, the stratigraphy of the fans. And I just brought you one example from Colosso. That's the fan which has been studied before because of its intercalating marine terraces. It's a town just south of Antofagasta. And you see here the fan on the orographic left side, they built a town on it, here not. Nonetheless, it's a street outcrop. You have a nice succession of alluvial fan material, but also intercalated marine sediments at the bottom, but also on top of it. And you have successions of intercalated Aeolian sand. Now, focusing on the alluvial fan deposits, and not only this, we mapped more and logged more stratigraphies. We could deduce that those fans are primarily built up by debris flow deposit and to a secondary degree also hyperconcentrated flow deposits, but even not sheet flow, the other, like as you might remember from Frank's talk in Mongolia. So here you have stratigraphic logs. At Colosso, it's largely indeed debris flow deposits. Okay, so we do have an idea about the types of the primary processes, but that's okay. That's something, but we want to especially understand more about their magnitude and frequency, and then also what are the controls on them. And for this, we dove into more geomorphometry. So what is traditionally can be used quite effectively in alluvial fans is the morphometric relationships between the fan and its source area. So here you see like relationships between catchment area and fan area and fan gradient from a quite recent review from Sam War of lots of groups of alluvial fans on Earth, but also from Mars and Titan. Well, this does, for a very obvious reason, not work for the coastal fans, because almost all of them are truncated by a marine erosion, sometimes the proximal latest medial part. So those relationships between fan and catchment do not work. The only thing which we can take a closer look at are the catchment morphometric parameters. And this is what we did. So I analyzed here 123 coastal alluvial fan systems along the 4 degrees of latitude. And you see here, maybe just a summary now as a profile from north to south. You see plotted in orange the alluvial fans, and you see in gray in background the mean topography, and you see some climatic parameters, basically, the mean precipitation parameters, increasing to the south. And what you can also see up here are 3 very prominent catchment morphometric parameters. One is the catchment gradient, a relief parameter, and its drainage density. And all 3 show quite strong, significant latitudinal spatial gradients. Now, those is kind of a spatial correlation, not yet a functional one. But we'll come to that because now the idea is, of course, to correlate that and check how do other allogenic environmental controls develop over those gradients. So one is certainly the lithology. Yes, here. And here we have our nice link during the first phase, the most important, I would say, with the Sernageomin, because together with Fernando and Paulina, we compiled 13 regional geological maps, 12 from the Sernageomin. You see them in the map. And that we were able to create for each of the catchment relative lithological compositions. and we do not see any relation, neither functional nor spatial, with our catchment parameters. That has been presumed in a further study, but by this confirmed that the catchment lithology does not play an important role. Neither do apparently uplift rates, but with the uplift rates I'm certainly a bit more careful because they're only very punctual. We are lacking large areas of uplift rates, and also sometimes the time range over which they are integrated differ, because those are only late quaternary uplift rates, but might be that entire quaternary or older uplift rates do indeed play an important role. But we are still lacking data. Now, the other point is what we checked is the frequency and magnitude of what could actually trigger those buildups, and those are high magnitude precipitation events. We know from the coast, from historical observations, that approximately at least 20 millimeters during a precipitation event are required to trigger debris flows. And so what we used within the CRC with our meteorologists in Cologne to make quite a high resolution reanalysis and to make a frequency analysis of those high and strong precipitation events. And this, here you see the results on the map, we also find the strong latitudinal gradient. So then we do have especially a spatial and functional relationship we could confirm between the catchment morphometric parameters prone and favoring debris flow occurrence together with climatic catchment environmental parameters. So that gave us some idea about the controls. Now, you might be asking now, you heard a short summary in Frank's talk, but how does that look now with the timing of the fan development? And there we need to deal with dating, of course. And dating those archives is challenging for several reasons. Might be the catchment materials, the mineralogy, might be simply the grain size composition. In the end, both has to fit, and the geomorphological situation has to be suitable, so it doesn't, for example, shouldn't be too complex in a way so that the interpretation might have too many flaws. So what we did in the first phase already tried to combine two groups of dating methods to get a better chance and to also be able to cross-check against each other. So we applied the group of trapped charge dating on the buried sediments that is luminescence dating of specifically feldspars. So it's here the infrared stimulated luminescence, but also the electron spin resonance dating my colleague Melanie focused on. And the other group is then not on the buried deposit, but on the exposed boulders to date those with terrestrial cosmogenic nuclides. And I won't go into detail, but we were able also to gain some methodological advancements. If you're interested in luminescence dating and trapped charge dating, feel free to take a look at Melanie's paper here, because she was able to, in a way, revive a bit the ESR dating method, which has not been used for decades, especially a lot on terrestrial sediments. And the nice thing is you can use the luminescence dating and ESR dating on the exact same material. So she compared those and could basically justify that it's also a robust dating method. Now, indeed, what we mostly use, because that's what we invested most in, was the luminescence dating together with the surface exposure dating. Now, we were hoping, of course, that on most fans we can apply both. The reality looked different. Usually, the fan was either suitable for dating by luminescence, but then you couldn't find suitable dating for exposure dating, or the vice versa. One example where both worked nicely and we could cross-check was the Quebrada de Iscuña. Here you see the stratigraphic logs, and we also have intercalated aeolian sands, which are nice material to be dated. We do have also, again, a paleo beach, which is buried at the bottom, uplifted quite some meters, but also some terrestrial material in between. Note what is barely ever possible to date is the debris flow and hyperconcentrated flow deposits themselves. That's just too coarse. Note, you see now both results, and top the luminescence dating of one outcrop, where that's at the front here, at this street outcrop, the marine sediments, some intercalated aeolian material, and just focus here on the one which is now in the incised channel, just 2 meters below the surface, given an age of 27 plus minus 3,000 years, and that is almost perfectly agreeing with our exposure landform age of our dated boulders on the surface. Our derived landform age clusters very nicely also at 32,000 years. So there we have an example where the cross-check worked very nicely. Now that's just one example. We were able in the end to date quite some more sites, and this is a compilation, the most current one, updated by a few sites over and over, of all alluvial fan deposits, not only ours, also I need to mention there were of course some datings before, especially in the Holocene ages by radiocarbon, relatively young debris flow deposits, but also from Diego Salazar, some thermoluminescence from archaeological remains, and this is the compilation. And note that basically we could not find any material older than MRS5, the last interglacial, which is preserved at the coast. That was a huge surprise for us, because especially if you think back of the Guarnios fan, extremely differentiated, but everything relatively young, and by that time we thought we gain much older ages if you compare to those Pliocene, Miocene ages from the Central Desert. No, obviously not. An exemption is at the Mejillones Peninsula. There you do find occasionally older material, but this is also a specific constellation because you have the protection by the uplifted peninsula, and you have a much wider coastal plain, let's say. So within the late Pleistocene, we could identify 4 phases of enhanced fan aggradation, and we could link them by comparing to regional paleoclimatic records to a primarily allogenic control on those transport-limited system by climatic fluctuations driven from the Pacific. So especially the Pacific moisture shores. We can explain for all those phases. For example, the LGM is very well known for northward shift of the westerlies since the mid-Holocene that might correlate very well with the onset of the modern El Niño. So this is what we deduced can explain this pattern, the temporal pattern, but also note that we do believe that an additional climatic control is very likely be in the sea level fluctuations, controlling largely, of course, the erosion base of those systems. Those are only the fan ages. I won't have time to go into detail on our additional age constraints on the aeolian activity and marine terraces. Just note that we were able to get quite some additional data on late quaternary uplift rates. I'm just mentioning this because it might be especially interesting also from the point of view of the Sernageomin. So there are also by our studies, we could date some more uplifted marine terraces. There had been done a lot in the 90s, 80s, 90s by Luc Ortlieb and the groups, but there are a few more now around. Okay, so we do have an idea about the timing, and last but not least, I want to give a few minutes on those post-depositional processes, the secondary processes, what happens after the fans were evolved. The nice thing is, going back to this compilation, we were able to date 2 fans with quite nice and robust morphochronologies by exposure age dating. So one is the Guarnios fan. It took quite a while, but we used this then as a chronosequence for weathering, because we do not then have, of course, exposure ages of the different surfaces, and then you can compare the states of the weathering of the surface. And at Paposo, where it's a bit wetter, there we also have a quite robust age model of those different old surface generations, and there we compared the state of their pedologic parameters. Now, first the Guarnios one. Here you see a summary of the morphochronology. Here an updated morphostratigraphy. If you combine it, you see, apparently this extreme differentiation occurred over quite a short time scale, just since the LGM, this entire differentiation into 4, if not 5 surface generations occurred. And if you look on those from the youngest one, sub-recent, to the oldest one, you see already by eye very apparent differences with regard to their color, so their spectral information, to their textural surface, to the surface roughness, which is much rougher here at the younger ones and smoother at the older ones, and also gravelometric, meaning the gravel size. And this we assessed systematically using high-resolution satellite remote sensing and drone surveys, and then we could establish the relationship. So again, you have here a summary of the morphochronology, also now with additional age data from the site. Here in this bar, you have a summary how we imagine how it was evolved. So build-up of the oldest, incision, build-up, incision, build-up, incision. And now we can plot our states of the weathering proxies against the age, and we see some evolution over time. So what we can deduce from it, on the one hand, are of course relevant processes. So for example, we deduce from the increasing spectral redness indices, formation of hematite, which you cannot see in the class, so weathering rim formation. Then you see both in the gravelometry, fining in the grain size, as well as in the smoothing of the surfaces, that you have a class breakdown, which leads to a smoothing of the surface. So if you eventually look also at a somewhat larger surface, scale of surface texture, speaking about the microscale instead of the nanoscale, that can also indicate some denudation of the original bar and swale morphology, very typical. So you have first the debris flow levees, and with the erosion at the end it all becomes plain and flat. And that's what you basically could see here in the fourth picture. And all in all, it seems to evolve a desert pavement. And this also over surprisingly small time scales compared to the central desert, so tens of thousands of years. And here at Guarnios, major changes occurred since the LGM. When we compare this to the regional paleoclimatic records, we could deduce that the primary climatic control in the weathering is less the actual precipitation events, because the weathering needs a constant moisture supply and can rather be linked to the fog occurrence. And the fog frequency and especially elevation band is largely related to the sea surface temperature and the sea level, less to the precipitation in general, coming from the Pacific. Now going to the south, I promised you to show you also the pedogenic parameters. Here we have this very nice, one of my favorite coastal fans, because it's almost half circular, very nicely shaped. And you have here our morphochronology. This Paposo fan seemed to be developed since the MIS5, so the last interglacial, and then the last abandonment, major one, about 60,000 years, plus minus error. Between those, basically the same principle. We use it also as a chronosequence, and here on each of those surfaces, we check 4 different shallow soil profiles. And in those soil profiles, you again can see by eye already changes. And what we assessed there systematically were the grain size, color, salinity, bulk geochemistry, and some other, up till here, that's pedogenic iron oxides. And now, looks complex, but you're introduced to this kind of scheme already. It's principally the same. You have the morphochronology and the idea about the genesis. Now we plot our states of the pedogenic parameters against age. And from this, we can deduce, let's start with the salinity. Although there's a strong outlier, it rather indicates a leaching in the topsoil of salts, something we would not expect from a hyper-arid environment. Okay, this might not be valid because of the strong outlier, but now let's take a look at the carbonates. We have a complete decalcification, which also goes hand in hand with a dealkalinization. So you have a first major drop of the pH value to a near neutral level only at the point the carbonates are soluted, which makes sense, and they can't act as a buffer anymore. But this is not typical for an arid, hyper-arid, also usually not for an arid environment. We have an accumulation of soil organic matter, and our pedogenic iron oxides, as well as spectrophotometry, show us that we have the process of an initial rubification, formation of iron oxide, specifically hematite, going on. What I skipped here is the texture. So because the loamification, the fine texture of the soil becomes more from a sandy into a loamy fraction developed, and goes hand in hand with increased organic carbon and secondary iron oxide, all very typical for the soil pedogenic process of loamification. This occurred over longer time scales than the weathering further north, so 100,000 years, major changes here between 60 and 50,000 years. When we compare this to our paleoclimatic records and how can we explain this, we deduce that now indeed precipitation again has to play a major role because we have largely leaching processes. Fog can't explain that stuff leaches through the soil profile. And luckily, very close by within the CRC, we have a weather station installed which ran not too long, but almost 2 years. And it captured quite some precipitation events and also the soil moisture. And it's known that at least the soil moisture of, let's say, more than 10% is required for any leaching to be possible to happen. And this threshold is only exceeded if a precipitation event of at least 3 millimeters occurs. I mean, it's not a lot. If you're here in the Mediterranean area or go to the south, and also especially not for us in Germany, but in the north, yeah, only a few per year might occur, but at least a few per year. This is the microclimate here at Paposo. You won't have several precipitation events at Iquique with this magnitude. Okay, now that's basically what we have as results from the coast. Just a very quick outlook what I'm currently working on, because still fun, story didn't end yet, because we have this at Paposo, this nice morphochronology. The idea, and the other thing is we still have big challenge to really decipher the relative importance of those allogenic controls. What we derive, as you've noticed, is based largely on a few sites where we draw a lot of interpretations. What I would like to do, of course, is like a much more consecutive, constant spatial record, more morphochronologies, to expand the morphochronology along the coast. However, dating is very expensive. Now there is a relatively cost-effective method with the Schmidt-Hammer exposure dating, and when one is able to calibrate it, one might be able to transfer it to some degree to other sites. And that's what I basically did last year in a campaign. We have now our morphochronology at Paposo, so I used this site to sample much more boulders there. What you basically do with the Schmidt-Hammer is you quantify rock hardness by a rebound of a normed spring bouncing on the rock, and then you get a semi-quantification of the rock hardness. And this I calibrated here and then transferred to many other sites to the north and south. Paposo is here, so I took 7, 8 sites, fan sites north of it and a few south of it. In the end, it were 19 different of those depositional lobes with different rock hardness values. Yes, I won't go into detail because it's all preliminary, but just so far, the results look quite promising, especially when using all 4 controlled surfaces we have. So we are not in the need of just making a 2-point calibration from H0 to 1 dated surface. We have the benefit, we do have a robust morphochronology with 4 control points, so why not using them? So this is this stepped, segmented approach. And by using those, we can have in the end, much more densified, expanded morphochronology for the south central part, so between 24 and 25 degrees south, let's say. And our first obvious seems that there seems to be some kind of clustering. So we have a southern sector where the response over time seems to be very systematic, and then a northern part where that does not work at all anymore. Why that's the case? I have some ideas. We're comparing, of course, again with other data, but that would go too far for today's talk. So to wrap up what happens at the coast of the Atacama Desert and why I hope, coming back to the intro, why I think it's worth to view it as a distinct environment from the core is because it has different ensemble of landforms, so morphography is different. the types and frequency of the fan processes I've shown you are different. You have strong latitudinal and longitudinal gradients in aridity, including the fork occurrence. The timing of the major alluvial fan evolution differs strongly from what's so far known from the core, so it's young, late Pleistocene. Processes as well as rates of weathering and soil formation are not typical for inland hyper-arid core deserts. As you've specifically seen, not with the weathering, it's physicals, a lot of salt, weathering with the karst breakdown. Okay, this can be, I would say, expected, but what we found very unexpected is that we have rather here at Raposo soil processes which are rather typical for semi-arid regions. Okay, so the second point is alluvial fans are challenging archives due to their complex morphostratigraphy, but yet still valuable geoarchives. And finally, despite the location at an active continental margin, it seems that as well as the primary genesis of alluvial fans, so their build-up, as well as their post-depositional alteration seems to be primarily driven by the climatic fluctuations driven from the Pacific. That seems to be, either might be moisture and or fog and or storm events. Okay, and with this, thank you very much for your attention. Also a summary of the some or most people involved, but as you've seen on the title page, there were so many names, and thanks to all of them for this constant support and help over those 8 years. Thank you very much.
Agradecemos a Janek. Tiempo para preguntas. ¿Alguna pregunta? Creo que en YouTube también tenemos alguna pregunta, quizá. ¿No? ¿No hay preguntas en YouTube? Sí. Juan Pablo.
Thank you. How you can discriminate for a deposit is a part of the fan or previous deposit with other characteristics? Maybe the basement of the fan, no?
Yes. What do you mean exactly with the
what difference lithologic, maybe?
Yeah, so it's a good question. In large parts you find if there are sediments below, usually a strong erosional contact, not always, but to a large degree that works. Now at the coast we largely have the benefit either the fans sit on the bedrock, so you have the often largely volcanic bedrock. We have a nice example just north of the Meriones Peninsula. Forgot the name of the caleta, but there you have an uplifted abrasion platform, so a wave cut platform about 6 meters, and it's bedrock. And so you really nicely see the contact. Or you have the marine material. What we never were able to find were below those marine gravels, so usually succession, if there are marine sediments, are the marine boulders from the foreshore, let's say, and then maybe on top some sand, so one knows, there was a transgression going on, and there might be somewhere the peak, and then the fan material. So they are very nicely differentiatable. Where it's certainly more difficult is when you go then into the interior desert. For the reason there you have a lot of older clastic material, also maybe fan material, valley fillings, let's say more, maybe not right away saying alluvial fan material, but some fluvial transported deposits, encrusted very often, also in depth. Then it becomes much more difficult. And I would even say the bigger problem in the core is the lack of nice outcrops. So at the coast with all the street outcrops, if you're in the north, I highly recommend taking the Ruta Uno at the coast, not always Ruta Cinco, because then you drive just past those and then you see a lot of those nice stratigraphy.
Okay. And for relative datation, we can very careful for the debris. Maybe have a weathering, previous weathering, no?
Previous watering?
Yeah, but is the datation is for you use in each debris, no? And maybe the debris is not very fresh always.
Yes. Yeah. No, that's a very good point. We find that a lot, so one needs to be careful also with buried material. Often it's stored for a while in the catchment, pre-weathers, and is then relocated. Yes, that's certainly a problem. Let's say usually in the buried sediments, when we focus on the matrix, the fine-grained, it usually gets overprinted. But especially with the exposure age dating, one needs to be extremely difficult. Which boulders to target and which to invest this expensive dating for, and which might be subject to previous weathering, previous storage already. Yes, that's what we kind of, with the exposure age dating, subsumize with the inheritance. So they have exposure and thus cosmogenic nuclides already inherited on their way, both during the exposure towards surface and during the transport way. Good point. Yeah.
Thank you.
Yes, and maybe the encrusted with salts could be another problem. That you do you say that too? Do you think that?
Yes, I mean, at the coast it's not such a big problem, especially in the south. It rather seems to be like a leaching of the salts. I mean, they will reoccur in deeper parts of the deposits, but if we now think of the whole fan stratigraphy and then, for example, Sala Grande and then the interaction with the salts, might be tricky for, I mean, you're more expert than I am on the interaction between the salar and the fans, but what we've seen together so far, it can be sometimes quite challenging. And we have really nice geophysical results along a transect of an alluvial fan going into the salar. You will get an idea during the next talk from Joel, and even there, it's not so easy to decipher, for example, there's the bedrock, there's now the base of the fan, and might be, especially in the interaction with the salar, quite some influences, the salt activity, some faults going through, maybe bringing brines up, interacting with the material.
Yes, no more questions. ¿Más preguntas? Haremos una pausa de 10 minutos y seguiremos con la charla de Joel Moura. Gracias.
Gracias.
Muchas gracias. Bueno, continuaremos. Llegaron dos preguntas más para Janek en el chat de YouTube. La pregunta es la siguiente, de Sebastián Muñoz Farías. Hi Janek, great talk. Can you see the same latitudinal distribution that is now controlling CAF also in the past quaternary CAF?
Greetings to Sebastian. I was thinking about the question because I read it before, because I can understand it in two ways. The one is kind of like still at the coast, but looking at the past climate. So, of course, what I did there with the gradient analysis, I mean, the lithology doesn't change over the quaternary, the bedrock catchment geology, but especially the climate, what you have seen and deduced from the singular sites. Unfortunately, we were hoping for, but that we couldn't get the data yet to evaluate with a sufficient spatial resolution past climatic simulations and reprojections of along the coast. So, for example, there are some were planned for the LGM. I think the results were even done, but we didn't have the chance to analyze them. That would be definitely worth it. From our general understanding of the system, I would expect yes, that the general longitudinal gradient should be there. For example, if I understand, if I got the results correctly from our meteorologist, for example, LGM, the westerlies shifted north, you have more frequent cutoff lows, but still they come from the south. So the further north you get, the more rare it is. But maybe everything is a magnitude more wetter or something. You had a different situation sometimes during the last interglacial or MIS4, that's rather argued to be due to a southward shift of the ITZZ, so rather more moisture coming from the equatorial regions of the Pacific. But as far as I know, during the late quaternary, there were no times where it came at the same time prominently, could be explained over a longer period from north and south, basically eliminating the gradient. So I would assume yes. The other question, or you could understand it, I'm not sure, it's rather asking about the older fans, which are older than the late quaternary. And those we find in the center, and this is actually the perfect transition to Joel's talk, because he will give more information how might be some gradients now developed throughout the core of the desert. Although the focus there, I can say that it's not a longitudinal, but rather a latitudinal gradient, how it devolves from east to west or west to east. Okay, that for first.
Another one. The question is, if you use software, for example, HEC, RAC, or for modeling, observing granulometry and water amount.
No, I did not. I know HEC-RAS. I did use it as a student, but we did not apply it for hydrological modeling. What we did were some hydrological connectivity assessments, so which were very interesting to see, but it's basically also a static assessment. How connected are separate parts of the catchment? It's in the end also basically a morphometric derivative, but it could nicely show that especially only the downstream parts of the catchments are the reactive ones. I didn't tell that when showing the nice results which worked with the latitudinal gradients, but those were only if you take those 50% of catchments which have rather usually the small ones, which are consisted of the highly connected catchments. If you include all the catchments which reach far back into the hinterlands, those catchment relationships do not show anymore. Apparently there's too long landscape evolution of those entire catchments, and basically what you're evaluating then are characteristics of the central Atacama desert already, and that then those do not work. I mean, that's not really hydrological modeling, but that's the closest what we went so far. Now more modeling comes on a longer time scale, so also not hydrologically, with the landscape evolution modeling. So some physical relations for the processes are behind those, but driven over a way longer time scale, of course, than the usual hydrological HEC RMS modeling.
Well, thank you again, Janek. Very nice talk. Now,
Thank you.
Joel Moren will give us his talk.
Yeah, thank you very much, Andres, and thank you also to the audience for staying for the third talk of this series, in which I will try to give a really condensed overview on the work that we conducted during the CRC 1211 CO2 phase 2, which is, I have to admit, still work in progress data. But you are invited to share your ideas on the data after the talk, if you want to. So, as an introduction, Janek has given a comprehensive overview on the coastal alluvial fans in northern Chile. And to me, one of the main outcomes of his studies is that, well, the activity of the fans that were studied range in a time frame between, let's say, 0 and 100 kiloyears. And on these time scales, actually climate appears to be the major driver of alluvial fan activity, despite the fact that we are actually in a highly tectonically active setting along the Atacama coast. And I don't know how much you're aware of the arguments going back and forth between climate and tectonics being the main driver of alluvial fan activity. But on the timescales that were investigated here, climate appears to be the dominant factor. And this is also imprinted in the catchment morphology, for example. This is what Janek just referred to in his last answer. So for plotting now the highly connective catchment, here a hypsymmetric curve. And what you can see here, basically, the more you go to the lower right, the more mature your catchment would be. And the further you go to the upper left, the more juvenile they are. And from the color coding, you can see that there is actually some kind of pattern between an increase in southern latitude and the maturity of our catchment. So also a connection between climate and the catchment, the catchment morphology. And all these findings of the first phase encourage us actually to make a step across the coastal cliff towards the hinterland, towards the hyper-arid core of the Atacama Desert. And when we do so when we now climb up the coastal cliff and have a glimpse across and look at the hyper-arid core, we see a landscape that has been subject to kind of heavily researched during the past decades. And a lot of this research crystallizes around the question, well, hyperidity, what was the onset of hyperidity, and more or less what was the history of hyperidity, how persistent was hyperidity over time. And here, for example, in a paper by Benny Ritter and colleagues, are some of these data shown, and as a kind of a review and also our own data, which highlights the history of aridity and the contradictive results on this history. However, regardless of what the onset was, an outcome is that the hyper-arid conditions were most likely punctuated by, let's call it, less arid conditions over time. So this gives us further motivation to focus on alluvial fans, interpreting these as climate archives, highly sensitive climate archives, to, well, capture maybe these punctuated periods of increased rainfall, increased precipitation, increased surface modification. And more recently, another paper came out, published by Laura Evanstein and colleagues, and they put on tackled the more big picture, the old question about aridity and uplift of the Andes, what caused what were the relationships between climate and the rain shadow effect, for example, of the uplift of the Andes. And they compiled a huge review paper with a lot of different data. And to our project, one of the most interesting outcomes is a kind of model in which it is postulated that the hyperaridity actually crawls over time towards the interior. From the coast, with ongoing uplift, the hyperaridity increases and migrates towards the east. And this is another strong argument for extending our research in the hinterland along a east-west transect, and also now for the third phase, including the Western Cordillera and Altiplano. What we are here for the upcoming 3 exciting weeks of fieldwork and some pisco sour. So what we do is we move eastwards, so we leave the Ratha and climb up the coastal cliff and focus on a study area that we call the Salagrande transect because it has the Salagrande in its center, and because it's an area where we actually can map and delineate and find a lot of alluvial fan systems. But as you can already see, there is a kind of spatial bias in the appearance of such systems, in the preserve, how they are preserved between the eastern part and the western part. So most of our systems are kind of clustered on the western shore of the Salagrande, with some systems north of the Chucolite fault system, and a few, it's hardly to see here on this screen, in the very east. However, we get a decent number of systems here that we can, for example, use for statistical analysis of our data, similar to what has Yannick done for the coastal alluvial fans. This has not been involved so much as, for example, for the coastal alluvial fans, but we are still working on it. This figure here you have seen before in Frank's talk, and we will now put some data on it. First of all, this is also unfortunately a bit hard to see on this screen here, as in characterization of the systems that we are working with here, the relation or the relation of fan area and catchment area. And what you can see, well, these orange circles, these are the systems that we are actually investigating here. They are smaller in size, which a bit kind of seems to contradict the theory Frank came up with earlier. However, a huge fraction of these smaller fans are located on the eastern rim of the La Manchas Mountains, which are debouching into the Salagrande and are actually kind of nibbled off and disintegrate into the Salagrande. So we are not really able to map the full extent of them. However, in terms of catchment size, we see that they are also on a smaller scale, which is actually could be a good thing because we would focus on smaller systems where the communication of climate signals from the source to the sink would be limited, so that we will not have too much, for example, transport processes in between, so that the small systems would more provide a better communication of these climate signals towards the alluvial fan systems that we then actually sample. Why is it always? Okay. So this figure here, Yannick has presented already as well. So the classical power relationships between fan area, catchment area, and fan gradient, which on a global scale, as Yannick has shown, appear to follow some trends, and which was not the case for the coastal alluvial fans. If we now have a look on the Salagrande transect fans, we see there is a significant correlation between the gradient of the fans as well as the catchment area and fan area. So this could be another indication that we got fairly intact sourcing communication pathways, enabling us, in theory, to use these alluvial fan systems as climate archives for the Quaternary, let's say. And we do so, Yannick has also already presented it, by means of measuring cosmogenic barium-10 from these alluvial fan surfaces. Yeah, so now let's put some ages on these surfaces. So we focus here along our transect on 4 systems. From west to east, these are SGT3, which is located close to, or in very near proximity to the Chumache Fault, so there might be some influence of tectonics here. But here we get an age of about, a mean cluster age of about 250,000 years. As you can see here from the age probability plot, we are suffering a bit from a low sample number, which is, well, partially at least, which is basically due to the quality of the samples. Well, maybe we're a bit too dumb to collect good samples, but usually the quartz, or what we think is quartz pebbles, well, mostly it's not even pure quartz pebbles, that we collect, they appear to have chemically impure quartz, which is not that suitable for our cosmogenic nuclide dating approaches. Also during etching, most of the stuff is microcrystalline. We lose it during the etching processes. Okay, so the next site in the Cerro de la Mancha, here we get 2 ages from 2 different surfaces, and this I should mention as well. Of course, with our dating efforts, we focus on systems where we see kind of a multi-phase development to get actually a multi-age control, to get a story of different pulses of activity from our alluvial fan systems. And what you can see here, well, I don't know if you can see it, the older surface, which would be somewhere over here, so this would be surface 1, gives us an age of more than 1 million years, while the younger surface, which would be here in darker brown, gives us an age of about 150,000 years. So quite an age discrepancy here. And finally, the last location where we could actually so far derive cosmogenic nuclide surface exposure ages would be the site 12, which belongs to a alluvial fan that debouches into the Salagrande, coming from the east towards the west. And here we got an age cluster for the older surface, which would be the whitish layer more or less here. And here we also get an age of about 1.5 million years for this surface. We got some additional age information as well here. I will come to that in more detail later. So there is one study by Baker et al. Who analyzed actually the westernmost fan system that we find in our transect in 2013 already. And there is age information available by a study of Carrizo et al. 2008, who dated a surface of one of these fans debouching into the Sala Grande from the west. We won't include this age into our age overview in next slide or so, because they used cosmogenic neon 21 for their dating method, so stable isotope, and they amalgamated their pebbles, so there is less information preserved here. Yeah, and it urges me a bit to put a stop sign here, sorry. When we are presenting this data, this is pretty much what Yannick discussed as a response to one of the questions that came via the YouTube. So what we do is basically we look at nice looking alluvial fan surfaces, and we look for pebbles, for datable material, quartz pebbles, and that would be the optimal case. And we take this pebble, and what we believe is that the cosmogenic nuclide concentration that we actually measure in this pebble was mostly retrieved when this pebble, or after this pebble was exposed to the surface. That is, after the debris flow event or whatever came to a still stand and the clast was exposed to the surface. And this is after what we collected and calculate an age from it. However, especially in hyper-arid environments, that must not be necessarily true. As Yannick already explained, there's a high chance of pre-exposure of an inherited component. For example, due to very, very low erosion rates in the catchment. This is also why it's so important to focus on small system, on small scale, spatially small scale system in this environment. There is there are several means to check for inheritance. The optimal case would be depth profiles, but it's pretty hard to dig these surfaces. Another method would be to sample the feeder channels of the alluvial fans or let's say the catchment outlets close at the apex, to get an idea of the inheritance that is stored within the catchment system. And for example, Baker et al. Did so pretty comprehensively. And in their fan system, they obtained an equivalent age of their channel infill of about 100 to 300,000 years. So this would be an age that you would need to subtract from the ages that you actually get from your surface. However, what makes us feel a bit more comfortable is that they sampled both pebbles and sand fraction. And it's the pebbles that give the younger age, so less inheritance in comparison to the sand fraction. We also sampled several catchments along our transect for different purposes, but also to assess the inheritance signal that we get. We also sampled these, of course, for all our core sampling sites, but we unfortunately were not able yet to measure them. That is to obtain enough datable quartz material. However, we get two locations where we actually could determine the inheritance component, which is our most east-lying system, where we get an age of about 100,000 years, a bit less than that, which is promising, while in a catchment that is here located more or less in the center of our transect, we yield an equivalent age of about 2 million years, which would equate an erosion rate of less than 10 centimeters, more likely, per million year. Yeah, so you see this is highly variable, and my feeling is that we actually need this data for every location that we sample. However, if we now plot our entire data set in a single plot, we see some kind of pattern. Our own data, that would be here now the 4 curves, and we also include the data from Baker et al. From the most westernmost catchment. And what we see is some kind of activity between, let's say, 400,000 Ka and 100,000 Ka, then an apparent gap so far, at least from the data that we managed to analyze yet. And then it sets in between, let's say, 1 million and 1 million, 1.5 million years ago. So there seems to be quite a pattern also on the different surface generations. Okay, and now before we leave Chile and move to Namibia, we put the spotlight on one of our key sites, SGT12. If it lets me, I will go back 2 slides. So to remember, the 12th site is the fan that debouches into the Sala Grande. And here we managed a pretty nice co-work with the geophysicists of the CRC, which were able to conduct a TEM survey across a transect and encompassing surfaces that we could actually date. So here the surface 1, here we got the age cluster. Well, again, only 3 ages, but here actually we managed to measure 6, but 3 of them were saturated. So what we get here, if we take the minimum ages to account for inheritance, we get an age of 1.5 million years. And then the lower surface, S0, here we get 2 individual ages of about 900,000 and 500,000 years. So if we now have a look at the TEM, at the resistivity plot here, you can infer, so this includes Sala Grande deposits. And what you can see here from the coloring, that you get a similar resistivity crawling more or less even below our alluvial fan surfaces. So what this may imply is that we got a minimum, by dating these surfaces here, that we got a minimum age of the desiccation of the Sala Grande, because our alluvial fan deposits cover the evaporitic sediments. Okay, so now we leave beautiful Chile and make a huge step across the Atlantic towards Namibia, which we try to study or try to see as an analog to also the coastal environment of northern Chile. And just to lose a few quick words on the setting here, so quite in contrast to the tectonically active region of northern Chile, where here the setting is located at a passive continental margin, which has undergone its main denudation pulse presumably during the Cretaceous. So it's a very, very ancient landscape, as Frank has already mentioned in his talk. Quite similar to the Atacama Desert, the aridity here is controlled by a cold ocean current. Here it's the Benguela current, and of course the latitudinal position of the setting with an associated subtropical high pressure cell. And there are quite a few other discrepancies between the setting that we see in Chile at the coast and the skeleton coast of Namibia. And one of the most prominent differences you can see, I hope you can see it, is the skeleton coast erg, which is basically a chain of dunes that has overridden some of our alluvial fan systems, of the coastal alluvial fans, and is actually also blocking sediment transport from the hinterland towards the Atlantic. Another important difference between the two study sites is that there's a lot of more water in the system here at the skeleton coast. This is basically also related to the fact that we don't have a rain shadow effect in the same manner as in Chile. So a few kilometers off the coast, you could get easily about 20 to 50 millimeters of rainfall. About 100 kilometers further to the inland, you may get about 100 to 150 millimeters. that implies that, that there is a certain gradient from the coast towards the hinterland. And this also implies if we have far back-reaching catchments, they capture a different climate signal than those systems that are located closer to the coast. And it also produces some fan types that differ from those that we find in Chile. Here an example, an aerial picture taken by Carmen Krapf of the Cochicrap fan, which is actually a braided fluvial fan. You can see all the channels crossing the fan surface here. What we did here now, as well as for the coastal alluvial fans in Chile, is to map all the fan systems that we could get hold of, which in this case were about 70. And as a first characterization of our systems, let's see where they plot in our fan area with this catchment area plot. Well, they are really in the upper right corner. So these systems are significantly larger than those that we find at the coast of the Atacama Desert and also along the Salagande Transect. So the morphometric, or as we may here better call it parametric analysis, is a bit more advanced than for the Salagande Transect. So what we did, similar to the coastal alluvial fans, is grab all the variables that we could think of, including precipitation, for example, and derivates from that, like precipitation peakness. And we also got a detailed geological map, geological data provided by the Geological Survey of Namibia. And if we now try, similar to the coastal alluvial fans of Chile, try to mingle them all together and investigate this data for some linear relationships, this won't be too meaningful because there may be some relationships, as you can see here from the intenser red and blue colors, doesn't matter what variables these are here now. But when it comes to partial correlation analysis, this won't hold anymore. And this is basically because we have different types of fans which have been modified after deposition. So as I said, we have the fluvial type fans, but we also see the skeleton coast erg which has overridden our fans. Then we have fans that debouch into the Atlantic, similar to the coastal alluvial fans in Chile, so that are cut. And finally, we have really differing catchment extents, which would capture also different, of course, amounts of precipitation. So this is a highly heterogeneous data set. And what we now need to do is kind of bring order into it, and by this we apply a hierarchical clustering approach. And so what we did first was to cluster all catchments based on all the variables that we used for the catchments individually, and also the fans individually. Because in a perfect world, we could relate these two clusters to each other one to one, which of course did not occur here, but we had about 50% of our fan and catchment systems that would be relatable. And the hierarchical clustering is also really efficient in terms of outlier removal. And we use the information that we got from the individual clustering to mingle all together to a combined clustering of fans and catchments. And this model will split us 3 clusters, which you can see here from the map, are actually more or less differentiable by, for example, their extent towards the hinterland in terms of catchment size, which would be a property of cluster 1. Cluster 2 would be fans and catchment that are a bit less confined, that also fans that evolve more freely. And for, cluster 3, you can see here, these are all the yellow guys. These are mainly those associated to the skeleton coast erg. And now we can use these clusters and do our partial correlation analysis within these clusters. Of course, you need to take care not to get too small clusters, but we got a decent N for at least the second and third cluster. And just two examples here, one of them for the third cluster, which characterizes actually this cluster. This is the elevation of, I think, on the y-axis, now hard to see, is I think the minimum elevation of the fan, and again, as a function of the minimum elevation of the catchment, so basically the apex. And what you can see is there is a really strong correlation for the third cluster, which appears to be logical because they are all more pretty similarly overridden by the skeleton coast erg, limiting our mapping efforts, of course. A more interesting result we get for the second cluster, here shown as the fan gradient as a function of the variable geology 2. And geology 2 are volcanic rocks. And this has been already proposed also by Carmen Krapf and co-workers, that the presence of volcanic rocks along the skeleton coast implies a higher fan gradient, because weathering product of, in this case, Etendeca rocks would yield smectites, while the Damara basement rocks, on which the adjacent fans or the adjacent catchment insides into, would weather or would produce clay minerals such as kaolinite and illite. The presence of smectite would increase the yield strength of the flow and thus increase the gradient of our fans. Okay, so to wrap this up, there are apparent linear relationships that we obtain by our clustering approach that we would not obtain if we won't cluster our systems. However, still similar to the coastal level fans in Namibia, most of our relationships are predominantly governed by the catchment morphometry. If we now have a final look on the textbook morphometrical relationships, so a similar figure as I showed in an earlier slide, but here now for the skeleton coast systems. Well, you would see, well, this is here the solid gray curve. You would see a weak correlation of fan area and catchment area, which is basically due to fan confinements, which we can prove by the fact that if we do the same correlation, which is, by the way, the only one out of all the other cluster correlations which is significant, gives us a better R squared, so a better correlation. If we just use or just consider the cluster 2 catchments, which, as I said before, are the more freely involving catchments. In terms of fan gradient and catchment area, we get a quite surprisingly high correlation, which is a negative correlation and basically indicates that increased water discharge, which is achieved by spatially larger catchments, because they extend further into the rainy zone, as I may call it now. And this would imply increased water to sediment ratios and vice versa. Okay, so now as for the chronology of these systems, we focused on 6 of these systems to put some ages on the surfaces. Of these, we have been now ages for 5 of them. And as you can see here on the right-hand side, well, you may not can see the x-axis here, this plot starts at about 1 million years. So younger than what we have seen. Well, actually it starts about 800,000 years, so an interpretation would be after the mid-Pleistocene transition. And the oldest and youngest fan surfaces, which would be indicated here by the thickness of the lines, is found on both oldest and young fan surfaces is found on fans with large catchments, so that reach really large into the hinterland. Basically, what I here attach to is also the grain size distribution, more or less, of a offshore core, which could be related with larger grain sizes to drier periods, which, as you can see with our data, we cannot really resolve. So our error ranges are too large, but which is more relatable to OSL ages, for example, which has been conducted quite a lot in this study area. And we also used a combined approach of cosmogenic nuclide dating and OSL dating on quartz sand. And just now for the last final slides, to give you an impression how different actually also this setting is from the coastal alluvial fans in Chile. We will now zoom in on the skeleton coast erg and focus on two sides, the Uniap and the Karo Gaisep, kind of sandwiching the skeleton coast erg. So this is another oblique view of the skeleton coast erg, which is basically a northwards convey of sand and sourced from coastline and river deposits, such as from the Cochihab, further to the south. And it provides sometimes only a temporary barrier against sediment transport towards the ocean. We do not have a direct age information on this skeleton coast erg yet. It is assumed that it's younger than the last glacial maximum. So we will now visit the Karo Gaisep, but on the way to the Karo Gaisep, we make a short stop on the Samanap fan, where we more or less impromptu sampled, let's say it's called a clayey outcrop, which gives us an age of about little ice age, like 700 years before today. And this is basically nothing special in this environment. This is just to show how much dynamics in this environment actually is. So how dynamic surface processes are here. And if you're interested in that, Eddie Walsh and colleagues have provide a really comprehensive overview on Holocene and late Pleistocene chronologies using OSL and carbon-14 and so on. So now we are at the Karo Gaisep, looking towards the skeleton coast erg, and you can really nicely see how the dunes, how the sand has overridden our fan. And similar to what we observed for the Samanap, we observe here an age discrepancy between our surface that we sampled with barium-10, yielding an age of about 300,000 years. While if we sample the channel wall just adjacent to this old surface and measure OSL, we get an age range of about 2,000 to 3,000 years. And we attribute this huge discrepancy to, well, kind of attachment of sediments to the channel wall, kind of slackwater deposit-like deposits that are deposited when there is a lot of water in the system that is actually blocked by the sand, and then creating a kind of a large pond towards the hinterland. And finally, the Uniapmund, which managed to break through the skeleton coast erg more permanently. Here, our combined dating efforts were much more successful. So we dated two surfaces, yielding an age of about 50,000 years, while with cosmogenic nuclide surface exposure dating, while with OSL we get a very, very similar age range about on an outcrop that spans about more than 20 meters of alluvial sediments. Okay, so I hope I could give you a kind of really condensed overview on the ongoing work that we are facing, trying different approaches of cosmogenic nuclide dating, for example, and also parametric analysis. And so, for example, here this curve here, the Cochihab surface, that was just added to our to our age chronology for the skeleton coast a month ago or so, changing our interpretation of this data. So I'm not keen on providing too much interpretation on well, climate-related cyclicity here that is reflected by our fans. However, what we do see are really different patterns of alluvial landform evolution in Chile against Namibia. The coastal alluvial fans ages or activity of that would be here in this upper field, ranging here to 300,000 years, more or less, including the Meriones one. And in comparison to that, the skeleton coast fans do show a much longer history of activity. And the Sala Grande transect here, our preliminary results are that we actually see a gap of fan activity, and despite constraints in space and time, both systems, Sala Grande transect fans and those found at the skeleton coast, both indicate fairly intact source-sink relationships as deduced from the parametric analysis. Thank you.
Thank you, Joel. Time for questions. There is some questions in the room. No? No hay preguntas en internet tampoco. Some comments? No?
Yeah, I mean, there's no solid interpretation behind it yet, so I can see that the base for discussion might be not that deep, but I mean, any comments, ideas on the interpretation of the data?
Maybe I don't know if the very complex problem in the Atacama desert, there is not that problem in the Namibia. I understand well that.
You mean in terms of inheritance?
Yes.
Yeah. Well, I'm always a bit cautious about that. So I would never exclude that there is an inheritance. And we also sampled channel pebbles there. They are not on the high priority list for processing, but we got some of the samples. What I showed for the UNIAP site, where we had similar ages for the OSL, 50 Ka more or less, and also for the surface samples, 50 Ka. That would be a strong indication for me that storage, at least for the UNIAP, does not play a significant role because of the age matching of OSL and cosmogenic nuclides. But in general, especially when we would focus on fan systems that have catchments that are not that far incised into the hinterland, I would always go for control samples on inheritance. Yeah. So to answer your question, I wouldn't exclude it. I think it's not that severe as in the Atacama Desert. I think in the Atacama Desert it would be the extreme case. But I think since there's more, the Namib is, there's more action taking place in terms of fluvial processes. I think it's less important in the Namib.
Yes, in general, the ages you get are coherent.
Yes, right. Yeah, I mean, in the hinterland of the Namib, there was a study by Collier et al., I think 2014, who showed that inheritance can play a role if there are quartz veins cropping out, which would erode at much slower speed than the surrounding environment. And of course, if we would sample these quartz pebbles afterwards, we may get an increased inheritance signal in these cases. But, well, in most of our catchments, in some of our catchment, there is basically they are composed of basalts and quartz-latites with a few quartz veins or quartz abundances. And I think in this case, it's not that important.
Okay. Yes, I don't see more questions on the internet. One question.
Thank you, Joel, because quite some of the data and your results of the most recent analysis were also new to me. Now, for Chile, for our now upcoming fieldwork, because we thought about applying some depth profiles for maybe both reasons, especially to get grasp of the inheritance, where would you place them? Also, realistically, we don't have super much time. It's lots of work. So I was, for example, the 12er side at the coast of the Salar. I mean, the older one, only 2 or 3 ages were not saturated,
Right.
but at least all 6 worked. So, and we do have a smaller cluster. So would you, for example, say, okay, they're targeting the younger surfaces?
If we have one shot, I would go for that.
Yeah.
Actually, I would also make it dependent, as you said, on the availability of decent quartz samples. Right? I mean, this. If we put all the effort in digging or digging a depth profile, we should do that in a system where we more or less know that there are some decent quality quartz samples that we could actually retrieve from these sites.
Yeah.
This should also play a role in our sampling.
Okay, so yeah, maybe we can also think about the Las Manchas one, because there quite some exposure samples worked, but we also, I think, yes, the inheritance sample from the channel did not. So maybe there's this chance for a second one.
Yes,
for
certainly.
motivated diggers.
Okay, and thank you, Joel. We will close the session. De esta manera cerramos la sesión. Les agradecemos a todos los que vinieron de manera presencial otra vez y todos los que siguieron la transmisión de Sernageomin, de esta primera serie, de la primera sesión de la serie de Geocharlas. Y los invitamos a que estén atentos y que sigan las redes del servicio para que se enteren de las siguientes charlas que vamos a tener. Porque vienen más durante este semestre y durante el año probablemente. Así que muchas gracias a todos y así termina esta sesión.